section 10.4, which is hypothesis testing for the population standard deviation. So one thing that's going to be different about this is that we don't have a chi-square test in the calculator for these types of problems. We will have to do a chi-square CDF, which means you will need to be able to determine if your test is right-tailed, left-tailed, or two-tailed. So let's look at this example here. One aspect of queuing theory is to consider waiting time in lines. A fast food chain is trying to determine whether it should switch from having 4 cash registers with 4 separate lines to 4 cash registers with a single line. It has been determined that the mean wait time in both lines is equal. However, the chain is uncertain about which line has less variability in wait time. From experience, the chain knows that the wait times in the 4 separate lines are normally distributed with sigma equals 1.2 minutes. In a study, the chain reconfigured 5 restaurants to have a single line and measured the wait times for 50 randomly selected customers. The sample standard deviation was determined to be S equals 0.84 minute. Is the variability in wait time less for a single line than for multiple lines at the alpha equals 0.05 level of significance? So let's go ahead and start off by writing out our hypotheses. This time the parameter in question is the population standard deviation sigma, which is known to be 1.2. So they want to test out if this new line procedure has less variability. It says that right here in the problem. So they did get a sample statistic that is less than 1.2, which is good because our sample evidence should be supportive of the alternative hypothesis, which is that sigma is less than 1.2. So because we have a less than, that means we're looking at a left-tailed test. So I'm going to draw a little sketch of the chi-square distribution. Our test statistic would then be over here in the left tail. And what we're going to do is find the area underneath the chi-square curve, and that area is our p-value. It is a probability. So we first need to compute this test statistic using the formula. So I have the formula right up here in the notes. Here. N minus 1 times S squared divided by sigma naught squared. So let's write that down. All of our tests so far have had test statistics. We've never had to compute them by hand. They've always been done for us in the calculator, but this one we do have to find by hand. So in this instance, the sample size was 50. So 50 minus 1 times S squared. S is the sample standard deviation. So we're going to square it. Divided by sigma naught squared. Sigma naught is our assumed population standard deviation squared. So let's put that in the calculator. Okay, so we're doing 50 minus 1 times 0.84 squared divided by 1.2 squared. Okay, so we get a test statistic of 24.01. Now because this is a left-tailed test, we know that that will be the upper bound in our chi-square CDF. So in the calculator, we're going to do a chi-square CDF to find the p-value. So to find the p-value, we're going to do a chi-square CDF. It's very similar to normal CDF, except you only need 3 things. You need the lower bound, which will be negative 1e99, the upper bound, which will be our test statistic that we computed, and the degrees of freedom, n minus 1. The sample size was 50, so the degrees of freedom is 49. And then we'll approximate that. So we're going to go to second, vars, and then it looks like it's going to be number 8, chi-square CDF. So the lower bound we said is negative 1e99. The upper bound is 24.01. The degrees of freedom is 49. Now, if your calculator doesn't have this additional screen, you just type it in as written here with commas separating each of the values so that it looks like this on your screen. And then we press enter and we get a probability, 0.001. I'll round it to 3 places. So that is quite a low probability. This looks like it's going to be statistically significant. Our alpha level was 0.05, so yes. So P is less than alpha. So we reject H naught. This means that our results are considered statistically significant, unlikely to occur if H naught was actually true. So that causes us to reject H0 in favor of H1, and we can now assume that there's less variability if they have a single line. So let's write a conclusion. There is sufficient evidence to conclude. There is sufficient evidence to conclude that there is less variability in wait time So variability is referring to the standard deviation, that there is less variability in wait time if they have a single line. So they may want to consider converting all the restaurants to having a single line so that their wait times are more reliable. Okay, so let's take a look at one more example. A researcher is studying the variability of heart rates in students during class. In general, the standard deviation of heart rate is 12 beats per minute. She obtains a random sample of students' heart rates. Based on this sample, is there enough evidence to say that the standard deviation of the resting heart rates for students in this class is different from 12 beats per minute? Use alpha equals 0.05. And note, heart rates are normally distributed. Okay, they gave us that note because this is a small sample size here. Well, actually, in general, in order to use a chi-square test of any sort, you do need a normal population, regardless of sample size. Okay, so we were given data values. What we're going to have to do is put these in list 1 in order to find the sample standard deviation. The sample standard deviation is in the formula here for the test statistic. So let's go to Stat, Edit, and type these into our lists. 61, 67, 75, 82, 86, 63, 71, 77, 83, 86, 64, 72, 79, 83, 89, 65, 73, 80, 84, 95, 65, 74, 81, 85, and then 95. That seems high. Okay, so what we want to do is compute the sample standard deviation. So we'll go to Stat, Calc, number 1 variable stat. So we've done this in the past. And then list 1, there is no frequency list, and then calculate. And the only thing we're really interested in here is S, the sample standard deviation. So let's write it down, we'll round it a little bit. S is approximately equal to 9.764. Okay, so notice that that is different from 12. In our problem here, it didn't say if she thought the variability would be higher or lower than 12, just that it would be different. And of course, 9.764 is different from 12, and it is lower. It's important to note that it's lower because for this two-tailed test, we'll need to do a little bit of extra work to find the p-value. So let's start out by writing our hypotheses down before we work on the p-value. Of course, the assumption is that sigma is equal to 12, that it's going to be the same for the students, and that her hypothesis or her suspicion is that it's actually different from 12. She didn't state higher or lower, so we're looking at a two-tailed test. Now, it's called a two-tailed test because the p-value, that area under the curve, occurs in both tails. Remember that p-value is the probability of getting your sample value or more extreme. So in a two-tailed test, that area occurs in both tails. So let's draw a picture. So this is less than the assumption. It's less than 12. So this value occurs somewhere in the left tail, and this is where our test statistic will be. So let's go ahead and compute that. And minus 1, so 25 minus 1 times s squared divided by sigma naught squared. Okay, so let's get this in a calculator. 25 minus 1 times 9.764 squared divided by 12 squared. Oops, I typed it in wrong. Let's get that back and fix it. That should be squared. Okay. All right, what did I do wrong? Try one more time. I think I've missed out on a parentheses over here. Okay, so here's our test statistic. It's about 15.889. So to find this area here, it would be a chi-square CDF, lower bound, upper bound, degrees of freedom. However, because this is a two-tailed test, you need to find the probability of finding that value or more extreme in both tails. So we also have to account for this area here. So we do 2 times chi-square CDF. And this will always be the case when you are doing a two-tailed test on a hypothesis test for standard deviation. So this will give us our p-value. Oops, equals. Okay, so let's go ahead and do that in the calculator. Second vars chi-square CDF. Well, you know what? Let's do 2 first. 2 times. Then second vars chi-square CDF. Whoops, went too far. The lower bound is already there. The upper bound is 15.889. The degrees of freedom is 24. Okay, so I have 2 times chi-square CDF, and here's the p-value. So it's about 0.216. Okay, the level of significance alpha was 0.05. So here, p is greater than alpha. So our results are not considered statistically significant. This means that if this were true, if the standard deviation was 12, it would not be unusual to get this sample statistic. So because of that, we don't have enough evidence to really be suspicious of H0, so we do not reject it. Okay, so let's write a conclusion. There is not sufficient evidence to conclude that the standard deviation of students' heart rates is different from 12. Beats per minute.